is 1. So you were asked to memorize that the limit of sine x over x is 1. Now you're able to compute that.
Oh yes, cosine 0 is going to be 1. Oh, 1. Surprise.
So what is the limit as x goes to 0 of e to the x minus 1 over x? E to the x minus 1.
It's going to be the limit of...
Write it down, write it down. Huh. E to the 0 is 1. Good. So when you plug in value 0, you get e to the 0. E to the 0 is 1. 1 minus 1 is 0. And then you plug in 0 here. You get 0 over 0. So we can take derivatives. Derivative of e to the x is e to the x, and derivative of x is 1. When you plug in 0 now, you get 1 over 1, and you get 1 again. See, when you have this problem, guys, there is no factoring or rationalizing. There is nothing you can do, right? Other than L'Hopital rule. Well, obviously, you can chase the value in a chart, and right, you can do that, you can graph. But if you are actually using algebra to compute these things, you would have to do this. So let's take a look at one of the infinity problems, right? You can have limit x goes to infinity of 3x squared plus 6 divided by x squared plus x minus 1. Now you should know how to solve this problem using chapter 2. You should know it, right? And you should know just by looking at it what the answer is. Anyone? 3. Exponents are the same, so you take the front coefficients, 3 over 1, so it's 3. But now, and you know to solve it by dividing everywhere by x squared and right doing all that cool stuff. But L'Hopital rule makes this even easier. If you are to plug in infinity for each one of your x's, you get infinity divided by infinity. And that's also what we call indeterminate form. Therefore,
what about the 6 in there? That would make it do infinity plus 6, or you think that would still be infinity, right?
Yes, infinity plus 6, right?
Yeah.
Good. So now we're going to take independent derivatives, which is going to be 6x divided by 2x plus 1. Now you look at this as a completely new problem. Plug in infinity, what do you get? You get infinity over infinity again. Well, that means L'Hopital again, right? So L apostrophe H, get limit, x goes to infinity. And now I have 6 divided by 2. Well, that's 3. We're done, right? So it's cool. So you must have 0 over 0 or infinity over infinity. Otherwise, the rule doesn't apply. Are we all agreeing on that? Let me write it in blood. Must have 0 divided by 0 or infinity divided by infinity.
Yeah. In order for this.
In order for the rule to work. Good. All right. I used exactly the wording you gave me. Except I'm going to be more dramatic. There we go. Bring some drama in. We are done with L'Hopital's rule. There are variations now that we get to enjoy. Certain problems are going to have 0 times infinity. So we call that 0 times infinity case. This one can be converted into L'Hopital's rule, and then you use L'Hopital's rule. So is this L'Hopital's rule? No. But when you apply this algebraic witchcraft we're gonna learn now, it will turn the problem that is 0 times infinity into what you want. And what is the witchcraft I'm talking about? It is algebraic formula which states that f of x is equal to 1 over f of x. It's just algebraic manipulation. This one trick is going to change your problem into L'Hopital problem. So need to use this formula to change 0 times infinity into 0 over 0 or infinity over infinity. Depends which way it lands. So now let me give you an example of this. So let's say you have limit x goes to 0 of x ln x. And it's going to be from the right, obviously, because ln x does not have a domain on the left side of yx. So what do you get when you plug in 0? You get 0. And what's ln of 0? Very good. It's negative infinity. If you look at your ln x function, as you go towards 0, y value goes down to negative infinity. So this problem, right, this problem right here has 0 times infinity case, which is what we are exploring. So now what I'm going to do is I'm going to use the blue formula on this x. So this is equal to the limit x goes to 0 plus ln x divided by 1 over x. So what I did is I pushed that x from where it was down into the denominator of the denominator.
So it's the function.
Function was f equals x.
Divided by its derivative. What it looks like.
We didn't do any derivatives yet. This is just algebra now. So now when you try to plug in a value again, ln x, when you plug in 0, negative infinity. And what is 1 over 0? Also infinity, right? Mm-hmm.
Yeah, it's undefined.
And now you have infinity over infinity. So, hello, l'hôpital.
Negative infinity over infinity.
So L apostrophe H. Limit x goes to 0 plus. What's the derivative of ln x? 1 over x, good. And what's the derivative of 1 over x? Very good. So now, this turns into the limit x approaches 0 plus of x, which is 0. Yay!
Let's see. That'll be x squared in the numerator, and then negative x in the denominator. Yes, I see it.
I think this is really cool.
Sure.
That you get to divide, that you get to multiply 0 times infinity and get 0. Earlier we divided 0 by 0, we got 1. Then we divided infinity by infinity, got 3.
Would this not be negative x?
No. Well, it doesn't matter. When you plug in 0, it would be negative x, but when you plug in 0, it dies.
All right, so I can't put in negative x? And
Sure.
that would be incorrect?
You can put negative x.
All right.
Let's take a look at another one of these.
How did you know which part to move to the denominator?
Oh, it's called experience. In your case, you are going to hit the brick wall and then you switch them around and it works. But if there is any comfort in the statement I made, you can only mess it up once, and then the second round will be all right. So if you see that you're getting something that you definitely don't want to differentiate 1 over ln x. You would have x over 1 over ln x. I'm not saying it's impossible, it's just why, right? So if something that you are working on is not working out immediately, then just switch it, and it will be fine.
Switch it with,
Well, flip the other function, that's what I meant. Flip the other function. Let's go into homework assignment, pick up another one of these problems. And I don't think they are separating these anymore. They just, they used to have sections to tell you which problem belongs where. And now what they did is just took all the problems, 82 problems, and they just dumped them and said, find the limit. So it's like, good luck. This is what it looks like. They used to have it separated. These 6 problems are 0 over 0. These 6 are infinity over infinity. Now it's like, go. So you gotta browse through this stuff to find, there they are. 53, 55, 54, 56, 58. A whole bunch of cool problems. Ooh, I know you like secant x a lot, so let's do that. Problem 57. Limit as x approaches pi over 2 minus, so that's from the left. So limit as x approaches pi over 2 minus, and then the parenthesis is pi over 2 minus x times secant x. So that's our problem. Now secant is 1 over cosine. Cosine has a 0 at pi over 2, which means secant will have a vertical asymptote, so that has to be infinity. So what I have here is 0 times infinity. That's what we have.
how does that go again? You said that the value is when you plug in pi over 2.
When you plug in pi over 2 for each x.
Each of x.
So parentheses is going to give you 0, pi over 2 minus pi over 2, and then sine of pi over 2.
That'll be its vertical asymptote.
Yes, because cosine has a 0 there, that means secant has a vertical asymptote. All right, so now I have to flip one of these, right? Which one do I flip? If I flip secant, would that help? Secant in the denominator is going to be 1 over secant, which is cosine. And then cosine of pi over 2 is 0, and then you have 0 over 0. Yes! Right? So, let's go. We are using the trick to first, so no L'Hopital yet. We are using the trick to change the problem. Pi over 2 minus x stays upstairs. 1 over secant x goes in denominator. 1 over secant is a cosine, yes. So we are still doing algebra. Remember, you have to copy the limit every step until you get to use it. So I have pi over 2 minus x divided by cosine x. Now when I plug in my pi over 2, I get 0 divided by 0. This is where L'Hopital kicks in.
I think I might be falling behind with bits.
1 over secant is cosine.
Yes. Oh, yes.
The derivative of pi over 2 minus x is? The derivative of pi over 2 minus x is? Negative 1, good. And the derivative of cosine x is? Negative sine x. So now negatives cancel, and you get 1 over 1, and there it is. The limit worked out to be 1. Awesome, right?
And I'll do one of that.
Cool. Some of the problems will have infinity minus infinity. Did you ever wonder what infinity minus infinity is? Well, depends on the problem. Sometimes it's going to be 1/3. Sometimes it's going to... So it's going to be awesome. Welcome to Calculus. Hey, you signed up, right? So now I got to deal with infinity minus infinity equals to 1/3 somehow. Let's see how. Still skeptical, I see. It's like, nah, he's joking.
Say this value depends on the situation.
It depends on functions, exactly. And I can make infinity minus infinity be any number I want. Awesome.
It's a variable, essentially.
So let's take a look at the case. Before we get to do any of these problems, we know what to do. You grab the wrist of the hand, right, and then you just go in full circles to make sure you work out your wrist, because I don't want any injuries by the end of any of the problems. So stretch, stretch, stretch. One way, the other way. Do the fingers, right? And once we are stretched, shake it, shake it, shake it, shake it. And now, start a new page, each problem. Let's go. Remember that the only way to do L'Hopital's rule is to have 0 divided by 0 or infinity divided by infinity. Okay. Previous problem was multiplication. And we used the trick to change multiplication into division, and then we had 0 over 0, we can use L'Hopital, right? The problem started as multiplication. we made the division so that we can use L'Hopital. Now it's subtraction. How do you go from subtraction into division? You see, the path now is going to be longer than using one trick formula, because you have to go from subtraction of two expressions into a division of whatever two expressions in order for you to have 0 divided by 0 and infinity divided by infinity. Otherwise, no L'Hopital for you, right? So, how would we make this leap to change subtraction into division? What's the intermediate step as well?
We begin by assuming that this expression cancels is equal to 0, can't we?
No assumptions. So it's a procedure, and it's a logical procedure. So when I get a problem that we can look at, maybe it will be easier for you to answer this question if I had the problem given, so that you guys can actually think about rather, concrete example rather than just general case. So here's the limit x goes to infinity of x minus square root of x squared minus 3x. When I plug in infinity here, I just get infinity minus infinity. Right? The stuff under the root is going to be infinity. Square root of infinity is infinity. And then we have infinity minus infinity. So this problem fits. So I am supposed to do some witchcraft over here.
So you can add and subtract actual values to non-arbitrary values to infinity, but you can't subtract or add infinity from infinity, right?
Yeah. So what now? Are you ready for the path? All right.
We don't know what this is equal to.
We have to factor first, because if you factor, you make it into a multiplication. Then you use the blue formula to change multiplication into division, which is why this is going to have so many steps. So let's go. The first order is factor, then use 1 over f, then L'Hopital, and then you win, right? That's the way, like the path that we have to take in order to solve these problems. So we start by figuring out, hey, I have to factor. Well, I can factor x from the first one, which means that I should have an x in front of the square root, so I can factor x from both terms. Well, in order for me to have a x in front of the square root, I should have x squared inside the square root so that I can kick it out as x. So now that means that I actually have to factor first x squared inside the square root. But the second one doesn't have x squared. So you see, it's just a whole train of issues that we have to deal with. So we start by limit x goes to infinity, x minus square root of x squared minus 3x squared over x. What I did is I multiplied the last term by x over x.
Oh, I see.
So that I can have the x squared. Now I'm going to factor x squared. That's going to jump in front of the square root as x. Then I can factor x, and then I have finally got into multiplication. So limit x goes to infinity of x minus square root of x squared 1 minus 3 over x. So what I have done is I factored out x squared inside, and now that x squared is going to jump out in front of the root as x. And finally, I can factor out x, leaving 1 minus the square root of 3 over x in the parentheses. Yes?
Wait, did you mean to make that x minus x squared times, or no?
No, x squared was inside the root. When it jumps out, it becomes x. Because square root of x squared, right, they cancel.
Yeah.
And the root still stays over 1 minus 3 over x. Okay, so we're here now. Let's check the state of affairs. When I plug in infinity, what do I get? Well, clearly when I plug in infinity for x, I get infinity there. What's 3 divided by infinity?
Just one step back, please. Why is it, how does x minus x become just 1? Is it because, oh, I see, once
You factor x out.
yes, and once that happens, you have 1 times the square root, and that becomes the square root.
Yeah.
My mistake.
So how much is 3 divided by infinity? 0. And so this is now 1 minus 0. So what's the root of 1? Square root of 1 is 1. And then we have 1 minus 1? 0. Woohoo! Hey! We changed the whole thing into infinity times 0, so now we can use the 1 over f. So now use
0 again?
1 over f. What happened?
How does that become 0 again? You have negative 3 over infinity?
That's a 0.
Yeah. Right, of course.
So 1 minus 1 is 0.
Yeah. Square root of 0.
Square root of 1 is 1.
1.
And then 1 minus 1.
I see.
So now we have infinity times 0 and we use 1 over f. So we're going to kick x downstairs. If you like pain, try the other one, see what happens. And now, at this point, you have 0 divided by 0. This is one long transformation to get to 0 divided by 0. Now, you take independent derivatives and everything should work out. So this is equal to by L'Hopital, Bernoulli. Limit x goes to infinity, and now we have to take these derivatives. Well, at least denominator is easy at negative 1 over x squared. We have to take the derivative of the numerator.
Well, should we treat numerator with chain rule?
Yes.
All right. Okay.
Derivative of 1 is 0. So we copy the negative sign, and now we have a derivative of the square root. Now we know what the derivative of square root is. It's always 1 over 2 times the same square root. And then we take the derivative of the under the square root and multiply as a chain, which would in our case be 3 over x squared. Negative will cancel negative. And in order to solve this faster, we multiply top and bottom by x squared, which would kill these x squares. And
Negative 1 on the bottom then.
no, negative and negative canceled as well. So what you're left with is the limit as x goes to infinity of 3 divided by 2 square root of 1 over 3 over x. When you plug in infinity, 3 over x goes to 0, so the whole thing becomes 3/2. Yay! Infinity minus infinity worked out to be 3/2. Welcome to calculus. Now, what can I do? I can tweak things out, right? And I can change the 3 over here, maybe with a 5, and that might turn into a 5, maybe, right? But this was a long transformation. A lot of factoring, keep factoring, keep factoring, keep factoring. And then we use once we get the multiplication, we use the blue formula, algebraic trick, right, to change it into division. And then from there, we have L'Hopital. So that's infinity minus infinity case. Some problems are not infinity minus infinity. They're exponential. So we have 1 raised to infinity, 0 raised to 0, and a whole bunch of these forms that we also take in consideration. So now you have seen infinity minus infinity, and now 1 raised to infinity, 0 raised to 0, infinity raised to 0 cases. And you're absolutely going to love these.
Yeah.
Because they're all logarithmic solutions. You ln both sides, and then you follow those steps.
So there's going to be something that each of these values are equal to that.
Yep.
These are all undefined values, right?
So limit x goes to infinity of 1 plus 1 over x to the x. I mean, this has to be our first problem. It's one of the most important things in mathematics, actually. Now, what would that be? So you look at this thing and you say, well, obviously I'm going to plug in infinity. And when you plug in infinity, you get 1 to infinity case. Now, how much is 1 to infinity?
Exponentially greater than infinity.
So some people want infinity, some people want 1. Any other takers?
Yeah. It might be 1.
Might be 1. Anyone else?
So we're going to have something that's equal to...
Well, how about we go figure it out? Huh?
What way?
Calculating, using L'Hopital's rule. That's why we're here, right? So, what do we have? We look at this, and then we say, let's set this equal to y, leave some space for ln. And then we ln both sides. So, whenever we calculate y, that's our answer. So, from this statement here, y is our answer because we set the entire limit equal to y. Then we ln both sides and blah blah.
So it doesn't mean, it just needs to be, we just
Well, we need to calculate it. Now, we're going to kick the limit in front. And then use your favorite power rule to bring x in front of ln.
Oh, yes. How does this work again? Where you factor the x from
There's no factoring here, it's a formula. Drums the power in front of ln.
Oh. Okay. Right. I remember that now.
So now, plug in infinity, and you get infinity times 0. Right? ln of 1 is 0.
Yes. That's right.
So infinity times 0.
Right.
So we get to use f equals 1 over f. So ln y is equal to the limit x goes to infinity. Kick x downstairs, so we have ln 1 plus 1 over x divided by 1 over x. And now you have 0 over 0 finally. When you plug in infinity for x's, you get ln of 1, which is 0, and you get 1 over infinity, which is 0. So we are ready for L'Hopital. ln y is equal to the limit x goes to infinity and now we're taking derivatives. Denominator easy, always. Numerator, derivative of ln. We know it's a division. You copy the function as is in denominator, and you put its derivative in the numerator. And now when you multiply by x square, denominator is gone, that's gone, so we have negative 1 over 1 plus 1 over x. Oh, negatives cancel as well.
Yeah.
So now when I plug in infinity, when I plug in infinity, it becomes 1 over 1, which is 1. So I got ln y is equal to 1.
This is another. These cases are another situation where the value depends on the given function. Right.
All of them. The entire section. How do I fish out y from here? Because y is our answer.
Sure. The only way to use the y.
Use e both sides. Good. E both sides. ln and y would cancel. So y equals e to the 1, which is e. Y equals e. Therefore, the limit as x goes to infinity of 1 plus 1 over x to the x is equal to E. Guys, this is definition for E. And we just seen the proof.
Is it equal to B?
Yep. Proof of E. So next time someone tells you, what do you know? You should start here. The definition for E is ln as x goes to infinity of 1 plus 1 over x raised to the x. Now, just to make sure that they can't add anything to it, you also say, but did you know that limit x goes to infinity of 1 plus a over x to the x is actually e to the a? So if that 1, which is now a, if that a is 3, then the answer is e cubed. If that a is 10, then it's e to the 10. That's much cooler formula, right? Which you can get all other values.
I think we're going to run through it now with a our way.
The what?
Proof of
Oh, it's the same.
E of A.
Yeah, it's the same. Just dragging a throughout.
Okay.
Let's see another one of these wonderful problems with these. Something cute. Limit sine raised to the tangent. Beautiful problem. Love it. Limit x goes to 0. Sine x raised to the tangent x. This is problem number 78. You know what to do.
Yep.
Y equals the limit x goes to 0, sine x raised to the tangent x, ln both sides, swap the limit with ln, peel off the tangent in front of ln, and then go from there. So now limit goes in front, right, and then tangent x times ln sine x. And when you plug in 0, you get 0 times infinity. You know it's closer, right?
What?
You can see closer, right?
Oh, yeah. I can see it.
Can you? So now ln y is equal to the limit x goes to 0 and I have ln of sine x divided by 1 over tangent x. X goes to 0. ln of sine x divided by the cotangent x. And we finally have infinity over infinity.
What? Oh, right. Two.
So now I can take derivatives. ln y is equal to the limit x goes to 0. The derivative of ln, we write the function here. Its derivative goes on top. No, derivative of sine is positive cosine. Divided by derivative of cotangent is negative cosecant square x. Good. So now we have some trig identities to shovel around. This is limit x goes to 0 of cosine x over sine x, negative 1 over sine squared x. One of the signs will drop, and all we have is the ln of y is equal to negative sine times cosine. Ah, I forgot the limit.
I'm sorry, I'm with it again.
Catch up. Plug in 0, we get 0. ln y equals 0. E both sides. And y is 1. So the limit as x goes to 0 of sine x raised to the tangent x is equal to 1. Now the beautiful thing, yes.
Why didn't you start with the tangent x like on top of the numerator and then the ln sine of x on the bottom? So like, why did you put tangent on the bottom? Like,
Because it's not tangent, it's 1 over tangent.
yeah.
Because that turns into cotangent and it's easier to differentiate. If I place 1 over ln sine, then I have to differentiate 1 over ln sine. That's not as fun. If you just put ln sine x in the denominator without 1 over it, then it's wrong. Now,
I think we didn't just multiply e by 0, did we?
no, e to the 0.
0. Alright,
And I created a sine x to the tangent x graph, and look what you get. A squiggle, a squiggle, a squiggle, a squiggle, a squiggle. That's cool, right?
it is for decoration.
Yeah. Next time when there is decoration of something, instead of actually putting these things, you can just write the formula.
Have you ever tried like making like full-on pictures out of math equations?
Yeah, plenty of those done in demos.
You can do it.
It's-
It just
That's what like math really want.
Yes. There's a lot of cool. I showed, right, in class.
You can make a flower too, I think, right?
Mm-hmm.
Is that done now?
You can do a lot of cool things. Let me see if if Desmos is going to do. That's flop.
Which one did you use?
Use the 4 cosine 40. You can use any. The number of petals. So this is what you learn in Calc 2 actually, and then use it in Calc 3. So tonight I'm actually teaching integration over regions like this. So in Calc 3, you can tune in.
Depends on what it numbers.
So if you have even a number, then it's double amount of petals. If you are using odd number, it's that amount. So for 5, you have 5. If I put 6, it's going to be 12.
Yeah.
So that's but that's polar coordinates, and that's your last lecture in Calc 2.
For whatever reason, my Algebra 2 teacher in high school showed us that.
Yeah, because it's really cool.
Yeah.
It's math.
It wasn't like, it was just
Right.
for fun,
Bye.
but it wasn't